All right. Hi, everyone. Um, geometric sequences are something that we are looking at for the past couple of days now. I want to kind of give you a video a little bit to kind of see what we can do to kind of understand this a little bit. So let's kind of look at this and maybe walk you through this so you're not completely, you know, in the dark somewhere. So geometric sequences on our homework, let's say that we take a square. Okay, we had a square on our homework. And this is a one by one, so let's take what we call a square. Remember, a square is all sides are equal, are equal. And what that means, if we have a one by one square, that is one square unit. That's one square unit. Remember, the area of a square is length times width. Sometimes it's seen like s squared, and s can be any value you put, but remember, this is a square. So the definition of a square is all these are 180 degrees, or 90 degrees, I should say, and 1 times 1 is 1. Well, the question is that if I take this square, this 1 by 1 square, and the area of the square was 1, because of 1 times 1. And then I said, take this square and I want you to cut this in half. And if you cut this in half, you have 1/2. So that's one cut. And then I said, why don't we take that square again and cut it in half again? So that is 1/4. So we're going to add 1/4 to the mix. And then if we do it again, we make another cut. We have what we call half of that, which is 1/8. And then you do it again, 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 and again until you can't really much do it anymore. So you're kind of taking three cuts. So you're cutting it in half. You get the half of that. The area of that is 1/2. You take that half and you divide it by 2. You get 1/4. You take that half. You get 1/8. Now on the homework, I did say just the three cuts. So these three cuts, I want you to add them up. And out of curiosity, if you did one more cut, which is, sorry, 116, 116, that's 116. So 16 instead. And if you add all these four up, you're going to get a number 116. Well, 15 over 16. That is very close to 1, but it's not quite there. So what I want you to kind of experiment with and kind of discover is that if you kept on, dividing this by 2, dividing this by 2, dividing this by 2, you are going to, you're going to get to something. So let's see, that's 16. You're going to keep on. That's 32. That's 64. That is what, 128. And you're going to keep going and going and going. The question was, will this ever get to 1? If you sum up all these cuts, these fractions, will you get to 1? Now, I want you to kind of think about that because there's been a lot of kind of a converse. It's a very good conversation piece. It's very a controversial piece as well to kind of say, okay, if I add all these little half pieces, yes, they should be equal to 1. Well, back in when we get into limits or something like that, we had limits. You're kind of saying, okay, as all the things are add up to, let's say we are approaching infinity, that we're just keep on doing this forever. Will our function, which is this guy up here, will that be equal to 1? And that's kind of what we're trying to see. That's what we are trying to discover as you keep on going. So you're going to keep on going with these cuts and just kind of keep dividing this by 2. Will you eventually, will all these little cuts add up to 1? And some people would say yes, some people would say no, because you would apply a little bit of calculus to it. or just simple geometry. So that's one of the questions I kind of want you to discover. Is there a right answer to it? No. Is there a correct answer? A wrong answer? Well, you got to make sure that you're understanding what you're trying to do here. And for the next part, for the triangle, that you had the equilateral triangle. Remember, all these are equal for equilateral triangle. Now, if you if you had another one, the same thing, and then you had, let's say, uh, you add some more to it. You're kind of just telling me what's going on with the triangles. You're just adding triangles, but this is really the heart and soul one for a geometric sequence that I want you to look at. And when you are adding all these up, that is actually what we call a series. So really, this is what we call a series. Remember, a sequence is like 1, 2, 3, 4, on and on. But remember, a series is that we're just adding those numbers up. So remember, a sequence is that you have like a space in between, a sequence of events. A series is kind of when you're adding them up. All right. Hopefully that helps a little bit with the notes. Now, let's go through what we call a geometric sequence, because that really threw a lot of people kind of a curveball into it. And I have a correction that we got to make. So let's do a little pattern here. So let's do 3, let's do 12, let's do 48, and on. Now, here's a pattern. Now, what I want you to do is kind of do a little discovery and saying, hey, is there a pattern to get to here? Is there a pattern to get to the next one? Now, to do that, you're probably thinking, okay, this could be some sort of pattern. What if you didn't know it was a geometric sequence? Because I told you that. What if you didn't know it was a geometric sequence? How would you attempt to figure that out? Because there are other sequences out there. So let's don't jump to that quick. Let's do that in a minute. But let's take this sequence and say we're sitting here and we were trying to figure out what's going on with this. Do I see a pattern? Do I see what we call a pattern? So one way we can do it, well, remember we can take this number and we want to see what happened when we did that. And I think that was 4. Well, let's see about this. What if we take 48? What if we take 48 and divide that by 12? Well, we got 4. Okay, well, let's see if that's true here. If we go 12 divided by its predecessor, we got 4. Well, it looks like we have 4 when we are going backwards. So if we're going to go this way, we would multiply by that what we call the 4. So your R, or common ratio, which is just 4. Okay, one thing I want to make sure that we know about is this. Some of you were trying to kind of look at that formula that I gave to you in class, and I want to make a little correction. So I want to make a little correction. I want to kind of continue this pattern here. But what we're going to do, we're going to kind of manipulate this a little bit. So what I gave you in class was a sub 0 times r in minus 1. This was given in class. Well, think about this. This first part is a sub 0. What we're going to have to do is not call it a sub 0. We're going to actually call this a sub n, but we're going to change this to a sub 1 times r in minus 1. So when we were doing this, I actually wanted to go to a sub 0, but it's not true because a sub 1, you're starting with the first one, and that makes sense because you technically need to go one more to get to the next term. So this is actually what we should be using. There is one more formula or one more alternate of this. So this is the alternate of this. You can also use something like this, a sub n minus 1 times r. I'm hoping that you see the difference between these. You see the difference. The difference is that the a sub n, you're actually taking one step, and this is kind of where I got kind of mixed up on this one. I went a sub 0 because I was thinking about this one, but we wouldn't take the n minus 1 to the r. See, that's the only thing I did, and I apologize for that. So that was kind of like the idea that I did, but just to kind of confirm that this is the one that we will look at and have in our notes now. And so we will get rid of that a sub 0 and put the first one, which is just 1. So let's test this. Let's go ahead and do a little test to kind of make sure that I'm, not throwing stuff at you. So let's do this. So our test was, remember, it was 3, 12, 48. Boom, boom, boom. And let's say that this is a sub 1, a sub 2, a sub 3, and I want to go to a sub 6. Now, according to what we just found, we know that the r is going to be 4, okay? And a sub 1 is 3, not 0. What we're going to do is test this theory out. So we're going to take 48 and we're going to multiply by 4. And if you do that, do the math correctly, that's 192. Keep doing it again. So you're going to go 192 times our common ratio of 4. And let's see, that you get 768. 768. Make sure you check my math on that. And then I want to go next one. So that's 768 times 4, which is going to be 3,072. So that's our a to the 6th term. That is our a to 6th term. Now, what I want to do is kind of prove this to make sure that we are, our formula is making sense, because we can do that. So kind of going up here, let's think about this. So remember, our formula that we need to change here is still a to the n, but a to the 1 times r n minus 1. So let's think about this. A sub n, we're going to go to a6. This time we're going to put 3 in, not a sub 0. And we're going to multiply that by our 4. And we're still going to n minus 1, which is 5. And if you don't like that, remember it's 6 minus 1, which is 5. And then let's do some math here. So kind of do a little calculator. I'm hoping that you're doing a calculator at home to kind of check my work here. And if you do it correctly, this is going to be it's that. Okay? If you have your own calculator, hope you can do this. But it's the same thing. So the only modification, remember, I'm just saying, was this. So I got the 2 confused. So that's what I did. I just got this confused. Look at the difference between these. This one worked. This one works too. But you got to make sure you're subtracting the previous a, not on top. So just make sure that's a correction, and it's just 1, not 0, just 1, and that should help you out. Okay. All right. Another thing that I'm kind of want to think about here is, in class we went over what we call sigma notation. Sigma, another way it's called summation. So summation. No, summation is just the short for sum notation. Okay. So sigma notation, or sum. Remember, it's this little, looks like an E, or maybe a sideways M. And you kind of want to make it kind of fancy. Might want to practice this a couple times. It's not that hard. Just practice it. So remember, we had a number up here. We usually call that, sometimes we say, let's go to infinity. And maybe this is usually like n as your starting one. And this is kind of like a function. And what this is that this is where we are ending. This is where we are starting. And that we're putting our function. But we're not going to use infinity. Infinity is just kind of where are we trying to go with this. So I want us to try a couple of these. Why don't we try something like this? We try a sigma. Why don't we put a 10 up here? And why don't we start at 1? And let's do, what about 1? Or let's just say n. Terrible looking n. Now what we're going to do is say, okay, well, we're saying that if we start at 1 and we're going to 10, we're going to make this equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. So here's our start. Here's what we're going to end. And you would have to sum all that up. Now, as you go on with math, there might be a way to kind of get to develop what we call a formula with this. And that's kind of what I'm trying to show you as maybe we go down the math class, but it depends on the timing. It depends on the timing of this. So that's not 100%. It's not very pertinent to math right now, but I wanted to kind of bring this up because you will use this in another math class, like a Calc 2 class, to kind of for a series and function, series and sequences. If you want to look it up, it's called a Taylor series. And it's a Taylor series is a Calc 2. But anyway, if you're going that far, it's up to you. All right, so then I want to go over what we call a factorial. So that's kind of the Taylor series. So let's look at another one that's a little bit more interesting with this, which is called that factorial. Okay, so factorial is saying that, well, if I had, let's say, n to some term, so in factorial, this is what we call a factorial. I know it's like an exclamation mark, but it's called a factorial. And really what it means is that you're taking some number, so let's take 5i, for example, or 5 factorial. And what we're doing, we're starting with 5, and we're just going to be multiplying down. We're just multiplying down to 5, 4, 3, 2, 1, but this is multiplying. We're multiplying. So what if I had, let's say 1 factorial is just 1 times. And there is actually, on certain calculators, there is that factorial button. And I'm just trying to make sure I can kind of get to it for you and kind of show you. But see, some calculators will have it, some won't. So what if we did 4 factorial? That'd be 4 times 3 times 2 times 1, which is what? Is that 24? Well, on some calculators, like mine, for example, at home here, if I zoom in real quick here, it's actually, you can't really see that here, trying to get some light on the subject here. Sometimes this is not always that hard, but I know you can't really see that too well. I'll get some more light in here, but it's actually right there. Don't worry about it. But anyway, if I press that, I will get this in for that. So it's called factorial. Some calculators, cell phones, I don't know if the cell phone has it, but I think most of the scientific calculators do. But it's just this little guy right there. It's called factorial. But that's kind of what a factorial is. It's just saying, okay, if I had 10 factorial, that is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And there's just a lot there to kind of look at and see, but it's pretty straightforward. Let's see. Just for future, So if you want to kind of investigate this a little bit more with Factorial, a good way to see this, I want you to kind of try this. If you know that 5 factorial is that, and you divide this by, let's say, 5 factorial, you're probably going to think 1. But I want you to prove this. And I also want you to try this. What if I had 5 factorial all divided by 6 factorial? What do you think would happen of these two? Just kind of a little, kind of a little fun with this. Kind of a little fun with this if you want to, kind of, spark some interest with this. Okay. The last thing I want to kind of show you, just kind of let you know that I know that these formulas are a lot, but this one right here is kind of what we call the compounded interest formula. This is the compound interest formula. And this just means that if you take out some money and you want to build on it, and let's say you took out, let's see, we want to find the amount, and maybe we want to put $5 in. Let's say we put $5 into an account. Well, let's say that 100%. Remember, you're always going to have 100%. And we want to, let's do it with 4% interest. So we're going to do 4%, so 0.04. Remember, we're going to always divide by 100. So remember, just to let you know, 4%. And if you divide this by 100, that becomes 0.4%. You're always going to have to move this to the decimal over. And so the N is where you compound. So let's say this was compounded monthly. This was compounded monthly. So how many months are in a year? I'm hoping that you're going to say 12, and that'll be that. And then you would take that 12 and move it back up and move it here. And let's say you wanted to do it for 1 year. For 1 year. That's where you put the 1. So that's monthly. Quarterly, daily, annually is 1. Okay, just kind of an idea with that. And so that's kind of the idea with compound interest formula. There's also one called continuous, or it's called a continuously. And that's what we call I should just use A here. Example. So A equals, it's called the PERT formula. So it looks like this, which is A equals P E R T. There we go. This is what we call the compound continuously. That means it's just the basis. Remember, E is approximately 2.71. That's what E is. It's just another base for businesses use it when they want to show something that's it's just a letter that means, it's kind of like I. So not I, but it's kind of like pi. Pi, remember, is 3.17. It's another way of kind of expressing what an irrational number is, and that we can go through that later. But this is a different kind of formula. But if it was continuously compounding and not just compounded with a limited opportunity. I know that's kind of maybe a little bit vague to you, but I just want you to see these because, it's kind of nice to kind of see some of these formulas, because in business or on a job in a bank, when you try to, invest money or something like that, you want to know how it's being compounded. And that's always nice to kind of see maybe a formula that goes with this. But try not to get too dragged down with these formulas. Remember, this is just saying, but I really do want you to focus with the geometric sequences and kind of seeing what those are and going from there. I'm hoping that this helped everybody, and I know that I do apologize for the formula, the mishap on the formula. So I'm gonna go back to it here. This part right here, I just got these two mixed up. My fault. But just make sure it's going to be A sub 1, not A sub 0. Okay. Hopefully that helped, and hopefully you can do well on your homework.